Welcome to this presentation on lifting low-gonal curves for use in Tuitman's algorithm. So this was the topic of my master's thesis from last year, and so it is joint work with my supervisor back then, Wouter Castryck. So let me begin with some background on Tuitman's algorithm. So the basic question there is, given a curve C bar over a finite field FQ, how can we efficiently compute the zeta function of this curve? And the first general algorithm is due to Getlaia for hyperelliptic curves, and it's based on some kind of trace formula for Frobenius acting on cohomology groups. And his methods were quickly generalized to larger classes of curves by several people, such as Gaudry-Gurel and later Castryck, Deneuve, and Vermeulen. And then in 2016, Tuitman developed an algorithm in similar style, also with Frobenius acting on cohomology, which applies to potentially arbitrary curves, C bar, which come equipped with a map to P1. And preferably the degree of this map should be as low as possible. But there is a technical aspect in Tuitman's algorithm, namely you have to supply the algorithm with a lift of this curve to characteristic 0, so to some number field. You also have to lift this map phi bar, and they have to satisfy some technical conditions. And the reason for this is that all of the computations are done in the number field or in the p-adics, because over finite fields this doesn't work very well. And actually this lifting step is already implicit in all of these previous algorithms, but there it's completely trivial. So this only starts to become a problem with Tuitman's algorithm, and it's the topic for this entire presentation. So let me be a bit more formal about this lifting problem. So we will fix a number field K, for which the ring of integers mod p is equal to fq, and we will be lifting curves from fq to OK then. So we consider a planar curve over fq defined by a model of this form, and we will assume that the degree d is at most 5 and denote by c bar the non-singular model of this curve. We will let our map phi bar be projection onto x, and assume that this map is simply branched. So note in particular that this map phi bar is of degree d, so that the function field of the curve becomes a degree d extension of fqx. So now the lifting problem consists of finding a non-singular curve C defined over the field K, together with a map phi from C to P1, such that, well, first of all, we want to lift the curve C, so the reduction of C mod P should be isomorphic to C bar. And note that in particular the genus must be preserved by this operation. If you don't want to preserve the genus, then lifting is very easy, because you can just take any polynomial over OK, which reduces to this one mod P. But this will typically increase the genus, so that's not what we want. And secondly, we also want to lift this this map phi bar, so that the reduction of phi mod p should be equal to phi bar. And basically the approach will be to find some model of the curve over fq itself, which we can lift to characteristic 0 naively, and this will typically be a non-planar model. So before going over to the lifting, I need one more piece of background on reduced basis. So we will denote by fq of c bar 0 the integral closure of fqx inside of the function field. So this is a ring of rank d, because the function field is a degree d extension of fqx. And you should compare this with the ring of integers of a number field, of course. But now you have two patches corresponding to the curve above 0 and the curve above infinity. So there's a result due to Hess, which tells us how bases of one ring, fq's of this ring above 0 and this ring above infinity are related. So this theorem works over any field, so let K be a field and Kc a degree d function field. Then there exist unique negative integers r1 up to rd minus 1, together with a basis 1 alpha 1 up to alpha d minus 1 of this ring Kc0 over Kx as a module, such that if you want to find a basis over infinity, you just have to multiply by a diagonal matrix with entries x to the power ri. So this theorem works over any field, and for finite fields and number fields, it's also feasible to compute these integers and find such a basis. So you should compare this result with the Minkowski reduced basis. So basically these alpha I will then be a reduced basis, and these Ri are related to the successive minima of a lattice of the ring of integers of some number field. So we will not consider the integers Ri, but we will consider a shift. We will put Ei equal to minus Ri minus 2 and call these the Maroni invariants of the curve C bar with respect to this map phi bar. And the corresponding basis will be called a reduced basis. And just for completeness, these Maroni invariants satisfy the following two properties, namely you can order them, and then the largest of them is at most 2g minus 2 over d. And secondly, the sum of all of them is equal to g minus d plus 1. And both of these results, well, you can prove them with the Riemann-Roch theorem, and they have some counterpart in the number field case. So this second result, you can compare this with the fact that the volume of the fundamental domain of some lattice of a ring of integers is proportional to the square root of the discriminant. So, well, if you think of the Ei as the successive minima. And then the first result states that the lattice is not too skew, so that the largest successive minima is at most the absolute discriminant to the power 1 over d. Okay, now let's go over to the lifting procedure, and we will start with degree 3. So here the goal was to find some naively liftable model over the finite field itself. So it turns out that in this case there is a model of the curve C bar of this shape right here. So it's exactly as we had before, but we have some degree restrictions on these polynomials fi that appear. And I like to use the language of Newton polygons for this. So I say that this polynomial as a Newton polygon is pictured right here. So this basically means that, for example, the degree of this polynomial f0 in x is at most this quantity here, 2e2 minus e1 plus 2. And then the degree of f3 is at most this quantity right here. And the same thing with the degrees of these f1 and f2. So it turns out that if you have a model of this shape, then it's automatically liftable to OK. So if you take any polynomial over OK, which reduces to this one modulo p, and it should have the same Newton polygon, then this will be a good lift. Now the question is, how do we actually compute this model? And for this we rely on the Delone-Faddeev correspondence for cubic rings. So for me, a cubic ring R over FQX is an FQX algebra which is free of rank 3 as a module. So in the number field case, you can think of orders of cubic number fields. So there's a result from the 40s by Delone and Faddeev, which parameterize all of these objects together. So there's a canonical bijection between cubic rings R over FQX, considered up to isomorphism, and binary cubic forms over FQX, up to an action of GL2. And this GL2 action, it's basically linear substitution in these cubic forms. So in this bijection, this up to isomorphism, it's basically change of basis. So if you change the basis of the ring, then this will correspond to the action of GL2. So this also means that if you fix a ring R together with a basis, then you get a unique, well-defined binary cubic form. And there's no more action of GL2 involved. And secondly, I want to say that this bijection is very explicit, and you can also do this on a computer. So if I have some cubic ring with a basis, then I can just write down the multiplication table, and I can extract the coefficients of the cubic form directly from this. So now we will apply this result for the lifting. So we start with our cubic ring FQ of C bar 0 over FQX. So recall that this was the integral closure of FQX inside of the function field. And we will be applying the Delone-Faddeev correspondence to this ring, but we have to pick a basis, and for this we will of course take a reduced basis. And this gives us some well-defined binary cubic form, f bar in variables x, y, z. So now it turns out that this is exactly the model I pictured before, with this nice Newton polygon that we can lift to characteristic 0 directly. So first of all, if you look at the vanishing locus, then this will define a model of the curve C bar. And secondly, this is the polynomial we had before, so we can lift it to OK naively. And I want to mention, of course, that all of this can be done algorithmically. So you can compute these reduced bases, and we have implemented this in Magma, and it works very well in practice. So now let's go over to degree 4, which is kind of similar but a little more involved. So this time we will also be looking for a naively liftable model of our curve, and it turns out that, well, our curve C bar has a model inside of A1 times P2, has a complete intersection of two surfaces, Q1 bar and Q2 bar. And again, there's some degree restrictions on the coefficients that appear. So first of all, this Q1 bar and Q2 bar, they are quadratic and homogeneous in the yi. And then there are some degree restrictions on the coefficients in x. And again, I drew this with a Newton polytope. So for example, if you look at this vertex right here, then this tells you that the y3 squared coefficient in qi is of degree at most 2e3 minus bi. And the same for all other coefficients, which you can read off here. And what are these integers bi? Well, there are certain integers which satisfy b1 plus b2 is g minus 5, and they are uniquely associated to the curve together with the map to p1. And this is kind of a bad definition of this bi, but it will work for the purpose of this talk. So again, if you have such a model, then you can lift it naively to OK. So you will just lift these two quadratic forms, then you land in A1 times P2 over K, over the field K. You take their intersection, and this will be a lift of the curve C. But how do we actually compute this model? So again, we will rely on ring parametrization, this time due to Bhargava in his PhD thesis. And it states the following: there is a canonical bijection between pairs Rs, where R is a quartic ring over FQX, and S is a cubic resolvent of R, considered up to isomorphism, and pairs Q1 and Q2 of ternary quadratic forms FQX up to an action of GL3 times GL2. So what is this action of GL3 times GL2? So this GL3 action, again, it's just a linear substitution because these quadratic forms are in 3 variables. And this GL2 action does the following. So you have 2 quadratic forms, so you can add, for example, a multiple of one to the other and more general things, and this will be the GL2 action. And again, if you change basis of R or of S, then this will correspond to the action of GL3 or the action of GL2. So this also means that if I fix R and S together with the basis for both, then I get a unique, well-defined pair of quadratic forms in 3 variables. And so I haven't said anything about this cubic resolvent. So it's basically some cubic ring over FQX. And in our setting, the cubic resolvent of such a maximal order, this integral closure of FQX, will be of the same shape. So it will be some ring of the form FQ of C bar prime 0 for some cubic function field of this form, for some different curve. Okay, so how are we going to lift the curve now? Well, we will consider this ring FQ C bar 0 and its resolvent, which was of the same shape. So then we take reduced basis for both of them, and we apply this Bhargava correspondence, and we get 2 ternary quadratic forms over FQX. And now we have exactly the same thing. So if you look at the vanishing locus of both of them, then this defines a model of the curve C bar. And this is exactly the model we had before with these slanted Newton polytopes. So you can lift them to OK naively. And again, all of this can be done algorithmically, and we have implemented it in Magma. So finally, let me end with some closing remarks. So we also did the degree 5 case, which you can find in our article. But I didn't include it here because due to time. And also it's very similar to the degree 4 case. And this time you will be relying on Bhargava's parametrization of quinticrines, which is again more involved than the degree 4 case, but still possible. So secondly, I want to say that our algorithm works well in practice, especially if you combine it with Tuitman's algorithm. But I should say that the running time will always be dominated by Tuitman's algorithm, simply because computing zeta functions of curves is way harder than computing these nice models of the curve. I also want to say something about higher degree. So our methods are very much related to unirationality results of Hurwitz spaces, HDG. So this HDG is it's some kind of moduli space parametrizing degree D covers of P1 by genus G curves. And our methods to produce these nice models, they are very similar to the unirationality proofs of these Hurwitz spaces for D at most 5. But it is known that for D at least 7, these spaces are not unirational. So our methods will never work in this case. And in degree 6, it's not known whether these spaces are unirational. And also there is no sextic ring parameterization known, which is essential to our approach. And lastly, finding these good models seems interesting in its own right. So theoretically, this link between ring parameterizations and these good models works over any field. And in practice, if you want to compute this on a computer, then you can do this over more fields than just finite fields. So in particular, you can also do this over a small degree number fields. Okay, that's all I want to say. Thank you for your attention. And if you have any questions, I will probably hear them next week.